Those are the 4 features that increase the rate of a chemical reaction. Very important. You're going to take this into Year 12. This makes up the last inquiry question of Year 12 Mod 8, and it makes up the entirety of Module 5. Okay, so very important you understand the factors that affect the rate of a chemical reaction. Very good. So let's start with temperature. Now with temperature, what they're going to do is they're often going to give you a graph. You might see it before. Let me try getting the graph for you. Here you go. You learn best through questions. Since you've all already started Module 4, you have a minute to create a plan. Now, I'm not going to throw you all into the deep end as much as I do with my Year 12s, but when you see a 4-mark question, Annette, is there anything that you might want to do before putting your pen on paper to write the answer?
Plan out your answer.
Very good. So my tip to all of you is if any questions, this is applicable to science especially, if a question is 4 marks or more, you want to plan your answer. And it might seem counterintuitive, right? Planning your answer wastes time. But I promise you, when you plan your answer, you will not miss losing that 1 mark that usually happens to students when they just go straight in and brain dump it, right? So what I want you to do now is I want you to underline the key words here. Pranav, what are the key words in this question?
Yes, number of collisions. And then temperature as well. Different temperatures, yeah. Reaction rate to increase.
Okay, good. So that's what I wanted to hear, right? So you want to start by underlining all the key words, right? And so Annette, when you see a theory or a principle or a complex term, what might you like to do with a 4-mark or greater question, Annette?
Define it.
Yes, so one thing I'd want you all to do is define collision theory. And I promise if you do that, you'll probably get a mark straight away. 3 mark. The remaining 3 marks, where would they come from? How many curves do we see in this graph?
3.
Yeah, right? So doesn't that mean 1 mark for each curve? You need to explain each curve with 1 mark, right? So let's start by looking at these graphs. What are they saying? We'll start at the one at 0 degrees. What is this saying, everyone? Now, first of all, EA, what did I tell you EA stands for?
Activation energy.
Good. And what did we say? A successful collision only happens when A, you have correct orientation, and B, you have the activation energy. Now, I want you all to zone out. I want you to filter out the 2 other curves. Focus on that long, tall curve for me at 0 degrees. Everyone with me, right? What is this curve telling me in that? So I want you to describe what conclusions you can make from that curve.
There is a great number of collisions, but it all happens with lower kinetic energy than the required activation energy.
Very good. So here we have kinetic energy that's less than the activation energy. And so the first conclusion she's made is amazing, which is the majority of particles, that's why you see number of collisions the greatest at this point, have a kinetic energy that's less than the activation energy. What will that result in? Because remember, what does an explain question mean? You need to know your verbs really well. For explain, I'm going to give you all the simpleton explanation, right? Cause and effect, that's what we're looking for. And the way you know you're hitting cause and effect is you want to see words used such as thus, due to, as a result of, resulting in. That's when you know you're explaining something and not just describing it. Make sense? So what Annette's going to say is at 0 degrees, the energy curve represents the majority of particles have kinetic energy that's less than activation energy. This results in the majority of collisions being unsuccessful according to particle collision theory. As a result, there will be a low rate of conversion from reactants to products. Do you see how I used thus, resulting in my answer? Right? Now, I'm not here to spoon feed you how to write these answers, but I'm here to show you what a good template looks like, right? So the conclusion you've made is for 0 degrees, we said, majority of particles have kinetic energy less than activation energy. This will result in unsuccessful collisions, and that results in a low rate of reaction. Do you see how my plan looks, everyone? I want you all to focus on this. If an English student or a literature student were to look at this, would it make any sense to them at all? No. And so your plan should only make sense to you, right? I'm not asking you to write the entire answer in your plan. That becomes counterintuitive and wastes time. You need to have a flow chart so you can use, so when you're writing your answers, you can quickly look up there and you can see exactly what you're planning to write. Use the minimal words to convey the meaning, and that will save you time. And that's a skill that you're going to be building with me throughout the rest of the year. All right. Next, Pranav, your turn. Look at this graph and explain that to me. What happens with a 100-degree curve? What do we see?
We see that it's the number of collisions is less than the one with 0 degrees. It's less than the activation energy, right?
Okay, now this might seem a bit confusing. I want you to pay attention to this graph here, right? So what he's pointed out is the number of collisions is less. That's actually not quite the case. The overall number of collisions, I want you to look at these graphs. If you were to calculate the area under the curve, all of these graphs or curves should have a similar area. The shorter curves are thicker. Do you all see that? They're the fatter curves.
Yeah.
And so overall, the area will be the same. So what you need to understand is all of these curves have the same number of collisions. But all you're seeing with the peaks here is a number of collisions at a particular kinetic energy. So now we can see that majority of particles in the 100-degree curve are colliding at a higher kinetic energy. That's the first observation you should make. At 100 degrees, due to increased thermal energy, the particles are colliding at a greater kinetic energy that is closer to the activation energy. Do you all see that?
Yeah.
Right? And then you say, however, even still, have a look at this. Look at the percentage of that fat curve that is actually over the activation energy. If you had to estimate that, Annette, what percentage would you say of particles actually have energy greater than activation energy? Is it more than 50, less than 50?
Less than 50.
Yeah, so you can say, however, even at 100 degrees, the majority of particles are still colliding at a kinetic energy less than activation energy. As a greater area of the curve exists to the right-hand side of the activation energy, the reaction rate will increase compared to the 0 degrees curve. Something like that. Now, do you all know what these curves are called? These are very, very high yield in your exams. These are called your Maxwell-Boltzmann energy distribution curves. You will never need to identify what the name of this graph is, but all I want you to understand is this graph is going to get brought up a lot and likely will be brought up in your prelim exams. They love to bring this question in, okay? So make sure you know how to explain it. So, Annette, what would our plan be for the 100-degree curve? I want you to give me the flow chart of explaining it. So what would you say here?
That the kinetic energy is still less than the activation energy.
But remember, the question is asking you as temperature increases, how does reaction rate increase? You want to explain how it increases still compared to the 0-degree curve. So you can say at 100 degrees, more percentage of particles have kinetic energy greater than activation energy due to increased thermal energy. However, majority still have kinetic energy that's less than activation energy. And thus, we still majority have unsuccessful collisions. And so reaction rate is still low, but it is greater than that. Does that make sense? I'm going to zoom in here so you understand what I'm saying. You want to compare the curves, everyone. Otherwise, you're not explaining how increasing temperature increases reaction rate. Do you understand that? Good. So to sum this all for you, to look at these graphs and understand them straight away, all you want to see is what percentage of this curve lies to the right of the activation energy line. The greater the area of the curve that's over the activation energy line, the greater the reaction rate. Make sense? And now, Pranav, you're going to explain the 1,000-degree curve. What does this show you? At 1,000 degrees, what can you say?
There's more kinetic energy, like higher kinetic energy.
That's greater than the activation.
Activation energy.
There's an even greater proportion. You can say even about approximately 50%. So approximately half of the particles now have kinetic energy greater than the activation energy. What does that do to the number of successful collisions?
It increases.
Yeah, increased number of successful collisions. What does that do to reaction rate?
It's a greater reaction rate.
That's it. That's all you need to say. And then you can explain that by saying, as seen, with majority of area under curve lies to the right-hand side of the activation energy line. Good. And that's how you'd explain this question. Does that make sense? Do you see how we always link it to successful collisions? Always link it to successful collisions. And you always want to define collision theory. If you all do this, you would have got perfect 4 out of 4. Does that make sense? Any questions so far? Okay, the last thing I'll tell you all that it's good to write is when you have increased temperature, you want to say there is increased thermal energy, and thus we have an increased kinetic energy of our particles. Okay, so I guess the jump here you need to make is when there's increased temperature, the particles have more kinetic energy. You need to specifically mention they have more kinetic energy. And then you always link that to what?
Successful collision.
Yes, always link it back to successful collision, right? Do we have an increased or decreased number of successful collisions? Okay,